Introduction to Scanning Electron Microscopy, or SEM. The goal of a scanning electron microscope, or SEM, is to first focus a very small beam of electrons onto a sample, and secondly, detect the products that are emanating from that beam-sample interaction. In order to achieve our first goal, focusing a small electron beam onto the sample, we will have to become familiar with a few major components of an SEM. The major components will include a discussion of the electron gun, apertures, a condenser lens, deflection or raster coils, and finally an objective lens. In order to achieve our second goal, detecting the products of the interaction between our incoming primary electron beam and our sample, we have to become familiar with a few important concepts. They are beam-sample interactions and detectors. Another important concept will be the major requirements and considerations for operating an SEM and getting good images with adequate resolution and contrast. The major requirements are a high voltage source, low pressure, and sample conductivity. So let's begin with a discussion of our first goal, focusing a small electron beam onto our specimen sample. Again, the major parts we will discuss will include the electron gun, apertures, condenser lens, deflection or raster coils, and finally an objective lens. The electron gun is the actual source of the electron beam. Its purpose is to provide a stable beam of electrons with adjustable energy. A thermionic gun uses heat to extract electrons. Typically, a sharpened tungsten filament is used as the electron source. 0 to 10 volts is placed across two terminals. As current flows through the wire, the temperature increases. As it heats, the filament emits both photons and electrons. Only the electrons are accelerated further down the column, and the initial source size is on the order of microns. A field emission gun operates by having a potential difference or extraction voltage established between the tip and the first anode. The resulting electric field, concentrated at the tip, facilitates electron emission, and a second, grounded anode establishes a potential difference to determine the accelerating voltage of the gun. The accelerating voltages used to accelerate electrons down the column typically range from 1 kilovolt up to 30 kilovolt. That's 30,000 volts. Apertures are typically very small metal discs with micron-sized holes in their center. The apertures serve to prevent outer parts of the incoming electron beam from continuing down the column. Because the beam must pass through these apertures, changing the aperture size has a direct effect on many important parameters. These include lens aberrations, resolution, depth of focus, and probe current. The condenser lens is an electromagnetic lens which controls the diameter of the electron beam. Though it may be logical to think that the condenser lens decreases the beam diameter, it may actually increase it. A full discussion of electromagnetic lenses will follow shortly. At this point, it's worth discussing some similarities and differences between glass lenses and electromagnetic lenses. In a glass lens, such as those used in a magnifying glass or optical microscope, there are a few important parts to consider. First, an object is the specimen or sample of interest, and it creates an image on the other side of the lens due to a path taken by rays of light or photons. So, glass lenses, and all optical lenses for that matter, require the use of a light source. Secondly, lenses of different thicknesses have different strengths or magnification factors. Thirdly, changing the distance between a glass lens and the object being observed will result in a change in magnification and focus. So, if we wanted to look at something with an optical or glass lens at different magnifications, we would have to have multiple lenses and be able to adjust the working distance, the distance between the sample and the lens. Electromagnetic lenses, sometimes called electron lenses, are similar but different. First of all, the object in this case is not the sample you are investigating. In fact, you have to flip this mental picture upside down. In the optical lens, the light was emanating from the object, which happened to be your specimen of interest. In an electromagnetic lens, however, the object being imaged or demagnified by the lens is actually the source diameter of the electron beam as it exits the electron gun. Now, by image, we don't mean what you see on the screen. We simply mean the electron beam as it appears on the other side of the lens. Secondly, thicker glass lenses have larger magnification factors due to refractive indices and the ways that light bends as it travels between two substances of different density. Electrons, however, do not travel so easily through materials, so electromagnetic lenses are hollow in the center. There are in fact stationary lenses whose strength can be varied by altering the amount of current that runs through them. This works because an electric current through a coiled conductor creates a magnetic field in its center. The strength of this field serves to reshape the electron beam. Lastly, changing the distance between the sample and the objective lens does not change its magnification. It simply changes the focus. In other words, coarse focus is done by moving the sample closer or farther from the electromagnetic lens, and fine focus is actually done by adjusting the current that is sent to the last lens that the electron beam passes through before interacting with the sample. So, you may be wondering, what about magnification? Well, again, perhaps contrary to initial logic, an increase in magnification is actually nothing more than decreasing the size or area over which the electron beam travels or rasters across the sample. Deflector coils are various groupings of coiled wires which act to direct the electron beam in various x and y directions so that the beam will effectively raster or sweep over a certain area of the sample. The beam is rastered from left to right and top to bottom, just as one would read the text on a book. At each beam position, there is one beam specimen interaction and one signal captured by the detector, and thus one pixel produced on the monitor. Because a detector takes the signal intensity from a specimen pixel and converts it to a grayscale pixel value on the monitor image is simply a 2D rastered pattern of grayscale values. Also, as previously mentioned, the raster area size is intimately related to magnification control. The objective lens is another electromagnetic lens which serves as a final fine-tuning of image focus. It does this by adjusting the final shape of the electron beam and by adjusting the focal point of the beam so that it converges to a single point on the specimen surface. Okay, we've now achieved our first goal, focusing a beam of electrons onto our sample. We achieved this by creating an electron beam with our electron gun, occluding parts of the beam with apertures, demagnifying the beam with a condenser lens, rastering the beam with deflection coils, and finally focusing the beam with an objective lens. Now let's turn to our second goal, Detecting electrons and other particles emanating from the beam-sample interaction. Let's begin with the discussion of beam-sample interactions. There are many particles or energies which can be detected after an electron beam interacts with a specimen or sample. These include, but are not limited to, backscattered electrons, secondary electrons, X-rays, Auger electrons, transmitted electrons, and cathodoluminescence. However, for our purposes, we will only concern ourselves with the first three: backscattered electrons, or BSEs, secondary electrons, or SEs, and X-rays. Backscattered electrons are actually electrons that originated from the incident beam, and due to interactions with specimen atomic nuclei, they have reversed direction with minimal energy loss. This is considered an elastic event because most backscattered electrons retain more than 50% of the incident beam energy, and thus they can range from about 1 to 15 kiloelectron volts. Because of these high energies, backscattered electrons are capable of escape depths up to several microns. That is, they can escape from several microns below the sample. Another significant fact is that the number of BSCs emitted from a sample vary depending upon the particular elements that make up that sample. For example, elements with higher atomic numbers emit more BSCs, and thus they appear brighter after detection. After detection, this provides us with excellent compositional contrast. Secondary electrons are electrons which originated from the specimen surface atoms due to a transfer of energy from the incident beam. These secondary electrons are emitted when an electron from the incoming beam interacts with the specimen electrons, and the event is considered to be inelastic, since secondary electrons only have energies up to 50 electron volts. Secondary electrons, or SEs, have very shallow escape depths. Most of them range from 5 to 50 nanometers, and they actually tell us nothing about sample composition. However, due to a phenomenon known as the edge effect, edges and ridges on a sample have more of the incident electron beam traveling through a shallow depth. Thus, these edges emit more secondary electrons and appear brighter. For this reason, secondary electrons yield topographic contrast and provide excellent edge resolution. An X-ray is simply a photon or particle of light which happens to fall within the region of the electromagnetic spectrum that has a wavelength from 0.01 to 10 nanometers. X-rays are only emitted from a sample atom when a high-energy electron falls down to a lower energy level, and the vacancy which is filled by a higher energy electron is usually the result of a secondary electron being emitted from the sample. X-rays can have huge escape depths, larger than 50 microns in some examples. And most importantly is that X-rays provide characteristic or elemental contrast. This is possible because each element yields unique X-ray energy photons when higher electrons fill the vacancies. In other words, each element has a unique X-ray emission spectrum, which serves as a type of elemental fingerprint or marker. Thus, X-ray detection can be used to achieve elemental analysis and produce high-resolution elemental maps. Okay, so now that we have a good foundation for understanding a few beam-sample interactions, let's discuss how we can detect these emissions and turn them into useful information, such as an image on a screen. Though the position, orientation, design, and shape of electron detectors will vary from SEM to SEM, the operating principles do not vary greatly. There are a few components which are necessary to any electron detector. We will discuss these shortly. and they will include a scintillator, a light guide, and a photomultiplier. Other critical components include a photovoltaic cell and an amplifier. When either secondary electron or backscattered electrons are being emitted from a sample and headed towards a detector, the first thing they will contact is a scintillator. A scintillator is basically a phosphor-coated surface which fluoresces upon excitation. In other words, the phosphor surface, when struck with electrons, produces photons of light. For each electron that strikes the scintillator, one photon is emitted on the other side. These electrons are actually accelerated by a small bias to ensure that the electrons have adequate energies before striking the scintillator. Otherwise, the incoming electrons may not have enough energy to cause fluorescence and photon emission. A light guide simply does what it says. It guides photons as they propagate away from the scintillator and towards the photomultiplier. A photomultiplier also has a very descriptive name. This part of a detector produces a set larger number of photons for each photon that enters. The amplification or increase in photons is linearly related to the number of incoming photons. Once the photon signal is amplified, the photons strike a photovoltaic device which converts the photon signal back into an electric signal. This amplified electric signal is then sent to the monitor display and now represents some level of brightness, which can be further amplified by increasing the gain on the signal. This is done by operator control. Putting all this together, a detector receives incoming electrons, whether secondary or backscattered, converts them into photons, amplifies that number of photons, converts that signal back into an electric signal, and then you, the operator, can further amplify that signal by increasing the gain. This is simply done by changing the brightness of your image. The wider area of the image then simply means more electrons were emitted from that area of the specimen, but the overall whiteness of the entire image is set by the brightness gain. Lastly, we need to discuss some of the major requirements and considerations for effective use of an SEM. Again, they are high voltage, low pressure, and sample conductivity. We already learned about the electron gun and the fact that it requires high voltages in order to establish large accelerating voltages and electron energies as they move towards our sample. Thus, a stable, controllable, and tunable high voltage source is a necessary requirement for good SEM operation. A low pressure environment is very important for proper operation of an SEM for two main reasons. First of all, if we're trying to detect electrons emanating from beam sample interactions, then we don't want anything else to be in the chamber near or around our sample. In other words, if there are a lot of air molecules such as nitrogen, oxygen, and argon in the sample chamber, then there is a chance that they will be struck by the electron beam and give off electrons which would be detected by our detectors, but obviously not originating from the sample. This would be considered background noise and would not provide an accurate image of our sample. For this reason, the chamber pressure is usually kept down around 10 to the negative 7 torr. When compared to atmospheric pressure, which is 760 torr, this chamber pressure is about 10 billion times less than atmospheric pressure. This is actually achieved by use of a turbomolecular pump, which basically draws air out of the chamber. Secondly, if too many air molecules interacted with the tip of the electron gun, where the electrons are actually emitted, then the tip would be degraded as it became oxidized. This would quickly lead to a non-functioning tip and we would have no electron source. Also, it's again desired that the electrons have a clear path from the electron gun through the gun column and into the specimen chamber. For this reason, the gun chamber is actually kept at a significantly lower pressure, around 10 to the negative 10 torr. This is about 10 trillion times less than atmospheric pressure. This pressure is maintained by use of an ultra-high vacuum ion pump and also supported by the turbomolecular pump. Sample conductivity is an important consideration when characterizing a specimen with an SEM. Remember, we are bombarding our sample with a steady stream of fast-moving, energetic electrons. Now, though we know some of these electrons will return as backscattered electrons and some will interact to form secondary electrons, many of these electrons are actually conducted out of the base of the sample through a metal sample holder, through the stage, and then grounded. In other words, we always provide a grounding path for our excess electrons to leave our sample surface. The reason it's important is that if excess electrons accumulate on our sample surface, they begin to alter the path of the incoming electron beam and also add to background noise picked up by the detectors. This effect is generally called charging. The effect of charging on the image displayed on a monitor is that the images will appear to glow or cause streaks and distortions as electron production is artificially enhanced and the beam is unintentionally deflected. So, if a sample is non-conductive, charging poses some serious problems. One solution to this is to coat the entire specimen with an extremely thin conductive film. Typically, we use gold or some other noble metal and apply anywhere from 1 to 5 nanometers of metal onto our specimen. This usually corrects the problems associated with charging. However, it does present another problem. Coating a sample with a thin film of metal and trying to image it is similar to putting a thin sheet over a person's face and then trying to make out the finer details. If the layer is too thick, we lose some finer details. If it's too thin, we have image artifacts produced by charging. So there is a constant balance between charging and actual sample modification. Well, I hope you have enjoyed this introduction to scanning electron microscopy and discussion that range from critical components integral to SEM to major requirements and considerations of operation. This investigation has taken you from the high voltage source, through the gun column, through the chamber, down to the sample, through the detectors, and onto a monitor. I hope this discussion was engaging and relevant to you all, and you can walk away having a better understanding and appreciation for scanning electron microscopy and the associated principles. Oh, I almost forgot to tell you about the last detector required for SEM characterization. It's you. Interestingly enough, as you view this screen, your eyes detect about 300 million pixels of information about 10 times every second. Then, the signal is translated into an electric signal, carried along your optic nerve before being filtered by the hypothalamus, and finally integrated by the occipital lobe in the back of your skull. A scanning electron microscope is an amazing piece of characterization equipment, but so is your brain and your 5 senses. So, keep using them. And if you want to learn more, keep your detectors peeled for more videos like this in the future. Be sure to check back on the Nano4Me website and consider becoming a member as well. Thanks for watching and learning.